Today I'm here to present a brief presentation on driver assist systems, also popularly known as ADAS systems. And these are the next generation of automotive tech and are currently a focus for almost all OEMs in the world. So let me go over briefly on the contents of this presentation today. My goal for today is by the end of this presentation, you should be able to have a high level idea of what ADAS systems are, what are the common features which almost every top OEM companies are currently manufacturing, and what is the logic and what is the sensor and interface behind those logics. At the end of the session, I will also go over the different fields and technical areas which you can focus on, and if you develop a skill set in those areas you can, and how you can approach a profession in this field of ADAS. And at the end I will also share a slide with the different companies and different supplier companies which are involved in this kind of technology today, and how you can target those companies for your career. So with that, let's start. So advanced driver assist systems, or known as ADAS. So these are systems and technologies which are developed by automotive companies to improve the safety of the driver and the passengers, and also the surroundings of the vehicle. And over the time, these technologies have evolved into something as a convenience for the drivers, and helping the drivers modern day car to make better decisions while controlling the vehicles, and hence increasing the overall safety of the car and the surrounding. ADAS technologies is one of the fastest growing automotive segments, at least in the current decade. And according to some research, the ADAS market size is poised to become worth of almost $140 billion USD by 2026. Recently, we have seen Euro NCAP. Euro NCAP is a regulatory body for new car acceptance and production vehicles, and they have mandated 11 driver assist technologies on all new cars manufacturing after model year 2022. Even recently, we have heard Union Minister of Road and Highway Transport of India working to mandate level 2 ADAS systems in the coming decade. And I will go over detail what is level 1, level 2 in the coming slides. But the overall idea is this technology is becoming very quickly becoming a very important part of the automotive technologies, and it's soon going to be standard in almost all production vehicles. So before I go into deep into ADAS, I want to touch base on how we look at ADAS and automation systems from an automotive point of view, or from an engineering point of view. So I'll be explaining how SAE has defined ADAS and autonomous vehicles in their definition. And so SAE is Society of Automotive Engineers, if you didn't know, and they define rules and regulations and definitions regarding automotive technologies. So SAE defines autonomous automation into total 6 categories, as you can see, from 0, 1, 2, 3, 4, and 5. So overall, you can see the 0, 1, and 2 are the 3 categories which are considered for human monitoring. And what does that mean is, if a vehicle has 0, 1, or 2 level of automation, that means the human driver is monitoring the environment. The human driver is completely responsible to see what is happening in the surroundings and react according to it and take control of it. Coming to level 3, 4, and 5, these are higher automated systems where the car and the sensor sets around the car are going to monitor the environment for the driver and are going to take some part of the control from the driver. So let's look at what is level 0. Level 0 means no automation. This is completely manual control, your generic vehicles, generic car, where the human driver is responsible for all the driving actions, steering, accelerating, braking, etc., everything, which is pretty clear and which is what majority of vehicles today on the roads. Coming to level 1 is driver assist. So in this level, there is some level of automation given to the vehicle. However, it is just an aid for the human driver. but the human driver is still the complete controller of the vehicle. And the best example for this I can give is cruise control. Cruise control is a common popular feature, which is where the driver can set a desired set speed or for the vehicle, and the powertrain and the brakes control the logic and try to maintain that set speed over the time. However, in cruise control, if there is some kind of an obstacle or some kind of a lead vehicle in front of your car, the human driver, is still responsible to brake and take control and maneuver the car accordingly. So it's a very low level of automation, but it is just an aid to the driver. Level 2 automation is called partial automation, and this is the category where maximum of the ADAS features come into the play. And what this means is the vehicle can perform some level of control and take some responsibilities from the driver. However, the driver is still required to monitor the environment and should be ready to take control anytime. And the best example I can give is adaptive cruise control. So adaptive cruise control is a feature where it's similar to cruise control, but in this case, the driver sets a desired set speed, but at the same time, the vehicle is capable to slow down and accelerate to any kind of leading target vehicles. So if there is a vehicle or any kind of object in front of you which is slowing down or speeding up, the vehicle will automatically brake and adjust the speed, and all the driver will have to do is to handle the steering and all the lateral control portion. So that is what ADAS, most of the ADAS systems will fall into, and we will see more of those in the coming slides. Level 3 is conditional automation. So in level 3, there are sensors and there are many different systems around the vehicle which are completely capable of taking all the driving responsibilities. However, they are only able to perform in certain conditions and in certain environments, meaning that the driver will have to still be vigilant and should be ready to take control, but the system is more than capable to take all the other responsibilities like steering, accelerating, braking. Only in certain cases, if the system is unable to perform, then the driver has to take control. And the best example today is, or which I should say, the closest example is the Tesla autopilot system, which is giving hands-free capability, and that comes slightly into the level 3 section. Coming to level 4, which is called high automation. Now, this is a vehicle which is completely capable of doing all the driving tasks without human interaction, but it can only perform in a geo-fenced area. What does geofencing mean? Geofence means that these vehicles are trained heavily for millions and millions of miles within a certain city or a certain radius of an area. Beyond that area, they cannot function. They can do all the driving tasks within the certain perimeter of area. And currently, we do not have any production vehicle or any company who is deploying level 4 automation. There are companies like Google's Waymo who are currently testing this technology in some cities like Phoenix, Arizona, and Los Angeles in California. So they are currently still testing it, but there is no company who has mass produced this technology yet. And the same goes for level 3 as well. So level 3 is also not regulated by any government in any country right now. So companies are capable of this technology, but due to regulations, we are not currently mass producing and selling it. And the final is level 5 automation. Level 5 is full automation, and as you can see by this image, like the driver doesn't even have a steering wheel anymore. So this vehicle is completely capable of taking all the driving tasks without any human interaction, and the human has no longer the need to monitor the driving behavior. Yeah. So we are in a process of coming from almost level 2 to level 5 in the next 10 to 20 years. And this gap is going to bridge very soon, very fast. And that is why people are so interested in ADAS technologies and how we can come from level 2 to level 5. So I hope you have a brief idea about how the automation systems are defined. And I'll be referring to these slides in the coming features where I'll be explaining the working of these features. So this is a very good information to have in mind. So let's classify these ADAS systems. So ADAS systems can be generally classified into two categories. So one is on the left, you can see active safety, and on the right you can see as convenience features. So let's start with the left column, active safety. So traditionally vehicles, what we have today, have two types of safety systems. First is passive safety system, and then there's active safety system. Passive safety system is a safety system which is able to protect the driver and the passengers after the accident or collision has happened. So the best example for that is airbags and seat belts, right? So those are passive technologies. Active safety systems are systems which are continuously trying to prevent an accident. So these consist of systems and warnings and alerts which help the driver to avoid an accident to take at the first place. And some of the good examples here are autonomous emergency braking, front collision avoidance, blind spot assist, driver alert system, wrong way alert, traffic sign recognition, cross traffic alert, rear collision warning, pedestrian detection. And these are just a few of the examples we have in active safety, but most of the companies have different marketing names, but they all come some way in the categories. On the right, we have convenience systems. Now, convenience systems are technologies which are produced to help the driver reduce their fatigue. So when the drivers are driving day to day, miles and miles and kilometers together, so there is a good chance of driver fatigue. So what these systems are designed to do are to take some of those responsibilities from the driver and help the driver to make better decisions on the road. And most of these features are your level 2 features, which I was talking about in slide number 4. So some of the best examples are adaptive cruise control, auto high beam, lane keep system or lane centering system, lane change and departure warning, assisted lane change, intelligent speed assist, and automated parking. And in the coming slides, I'll be explaining some of the features from active safety and how their logic works, and some of the features from convenience safety, convenience features, and how those logic work. And in the middle, you can see an overview of how the sensor systems are currently integrated in most of the vehicles. So these are the list of sensors we currently have, and all these sensors come into play to basically develop one or these systems. The first is a long range radar. A long range radar is generally fixed somewhere in the front of the car. Typically, it's below the bonnet and between the headlamps. And what the long range radar does is it helps in target tracking for up to 10 to 12 meters ahead of the vehicle. And the primary user of this sensor is adaptive cruise control. Also, some features like emergency braking and collision avoidance, those features also use this front radar. The second, we have LiDAR. Now, LiDAR is currently no automotive OEM is mass producing LiDARs yet. LiDARs have the similar concept as radars, but LiDARs use laser rays instead of radio frequency waves. And LiDARs are extremely expensive and currently not viable for mass production. So we do not have any companies who have currently produced LiDAR and on a mass scale. But LiDARs will be soon. Over the time, they will get cheaper and better and more compact, and we will be seeing those sensor sets. Then the third is camera. There are several different types of cameras around the vehicle. The main front camera is on the windshield. That is a front windshield camera. And this camera is used very heavily for features like traffic sign recognition, lane keep system, any sort of lane departure or lane centering system. It's also used for adaptive cruise control and some of these active safety systems, and also like features like auto high beam, intelligent speed assist use the front windshield camera. And there are other types of cameras. For example, a lot of automotive OEMs like to call it as surround view cameras or 360-degree cameras. What they basically do is there are different small cameras around the vehicle. Typically, there are two cameras on the rear view mirror, and there's a camera at the back of the car. They digitally enhance all the three image and stitch it together to give a surround view image to the driver. So the driver is able to monitor and see every object around the vehicle using all the three cameras. And of course, some of these cameras are used for features like park assist and reverse braking, etc. The fourth type of sensors are short and medium range radars. So short and medium range radars, unlike this main radar, has a field of view of 3 to 4 meters. And these radars are currently placed on all around the car, primarily on the rear corners and the front corners. And features like blind spot detection, cross traffic alert, rear collision warning, these features use these short range radars for their functioning. And at the end, we have ultrasonics. So ultrasound sensors or ultrasonic sensors are primarily used by all sorts of parking features, and you can see them all across the car. They have extremely small range, less than 2 meters, and they use ultrasound to function similar to radars, but they use ultrasound, and they are available all across the car. So these are the different sensors which we are currently using in production, and hopefully this has given a brief idea on which feature will be associated to which type of sensor. So going forward, I'm going to try to explain some of these features in these lists, and I'll explain how the boundary diagram is and how they are interfacing in the actual vehicle. So let's start with active safety features. And the first feature I want to talk about is blind spot detection systems, or popularly known as BLIS. So what is blind spot? Blind spot is any area uh, around the vehicle which the driver cannot directly see while in control of the car. And typically the areas which are blocked by the A and B pillar on the vehicle. So if you see my pointer, this is the A pillar and that's the B pillar, and typically those areas are inhibiting the driver's view while driving the car. So that those areas are called blind spots. And typically how this feature really works is there is usually a blind spot LED. There's an LED light. Some OEMs have it on the rear view mirror, some have it on the A pillar, or some have it directly on the speedometer cluster. And what happens is when there is a vehicle which is within the blind spot range, this is the blind spot range where the driver is unable to see currently, and if there is a target vehicle present, then these LEDs will be bright, they will light up, and they will indicate that there is a target present. And let's say the driver ignores this and tries to merge into the next lane and uses his or her indicators, the left and right indicators, then these LEDs will start aggressively blinking. And let's say even after these blinkings, the driver still attempts to go over the next lane in spite of a vehicle there, then we will have aggressive warnings on the speedometer cluster. So this is typically how blind spot detection system work. In the coming slides, I'll be referring to these two terms quite a lot. First is host vehicle and target vehicle. So host vehicle is nothing but our vehicle, the vehicle of interest where our driver is sitting, and anything other than that, which is a potential a potential cause of an accident or collision, we will refer to them as target vehicle. So just to have those terms out of the way, because I'll be using them quite often. So in this example, in this image, you can see that this is our host vehicle, and there are two target vehicles on both left and right of the left and right hand side of the vehicle. And in this case, the driver would be seeing both his left rear view mirror LED and right rear view mirror LED to light up. Now, at least blind spot detection has been there around for at least 15 years right now. And initially, different companies had different approaches. Most companies started with a side camera or a side radar, and over the time, maximum majority of the OEMs have now shifted to side radars because camera detections have different limitation because cameras don't work well in rain or snow or some kind of foggy condition. So that's why most of this OEMs have started using side radars. And side radars are typically installed somewhere second door or the passenger side door, and they are typically installed on both the sides of the car. In the next slide, I'll be explaining how the boundary diagram of blind spot assist works. And every almost all the boundary diagrams I'm going to show you today will look something like this. So they will typically have three areas. The first area is the driver. The driver is our main point of interest, and he's out of the vehicle, and any interaction with the vehicle or any interaction from the vehicle to the driver will be indicated by these arrows. The second area is the vehicle itself, the physical vehicle, and all the components inside the vehicle. So typically there will be an ADAS controller, there will be some kind of sensor set, there will be a vehicle model, and of course there will be the HMI or human machine interface. So any sort of warning or image or cluster chimes, those will come under HMI. And the third is the environment. So the environment is again outside the vehicle. Any kind of environment consists of any object or target vehicle which is cause of a potential accident or a collision. It comes under environment. So let's start how blind spot assist works, and we'll start from the environment. So in this case, your environment is your target vehicle. Let's say there is a target vehicle on the left hand side of the road, and it's currently in the blind spot area of the car. So what will happen is this the left corner radar will detect the target vehicle, and I'm not going to explain too much into how radar technology works, but I'll briefly go over it. So radars work by transmitting radio frequency waves, right? So typically the radio frequency waves will be transmitted and it will hit back to the target vehicle and will be reflected from the target vehicle body back to the radar. And there's a concept called Doppler shift, and this Doppler shift is used to measure all sorts of information like how far the vehicle is, how fast the vehicle is coming, and how big or what's the size of the vehicle which is there on the blind spot area. So all sorts of that information is collected by the radar, and each radar has its own individual ECU. So there is an ECU for the left and there is a separate ECU for the right. So the left radar ECU is going to take all that information from the Doppler shift and it's going to process the signal processing algorithm, and it's going to collect different informations on what's the speed of the target vehicle, what's the distance of the target vehicle, how many target vehicles are there, because there's a good possibility that there will be multiple vehicles in the blind spot area. Depends on what vehicles they are. They could be a two-wheeler or a four-wheeler. So all that calculation, all that logic is in the radar ECU. And once all these targets are achieved, the signal or the information is then translated to the ADAS controller. And within ADAS controller, there are two segments for blind spot detection. First is the sensor fusion and multi-target track. Okay, so what does sensor fusion mean? In all these ADAS systems, we have multiple sensors which are typically reading the same information. For example, the left corner radar and the right corner radar both are tracking objects or target vehicles. But the sensor fusion algorithm, it takes all that information and processes it in such that it's going to categorize which target is more important or more threat to say, and it's going to classify all the targets into different categories. For example, if the target is very close in the blind spot detection area, then it will be categorized as category 1 or category 2, and it's going to track all the targets. And the sensor fusion algorithm needs different type of inputs coming from the vehicle. And that is what vehicle model stands for. When I say vehicle model is basically all the information about the host vehicle, like what is the current speed of the host vehicle, what is the size of the host vehicle, what is the weight of the host vehicle. So all those information are stored in the form of a dynamic vehicle dynamics equation, and all that vehicle dynamics information is also fed into the sensor fusion algorithm to detect and do the multi-target tracking. So now all the radar information is in, the vehicle model information is also in, and our target or sensor fusion target tracking has detected all the targets. Now that information goes to the blind spot logic. And what this does is, this is what controls based on the category of the target. This will determine whether or not the driver is at risk or the host vehicle is at risk. So it does a threat assessment, and accordingly it will send the CAN signals to the LED mirrors or the cluster chimes. So cluster is nothing but the speedometer display which you see. So we call that cluster, instrument panel cluster to be precise. And that is all that information is given into the HMI, into the cluster chimes or LED lights.